Hi, my name is Sharvil Kumar, and I'm from the University of Louisville,
My name is Nguyen, and I'm from Penn State University.
and we are excited to share the project we've been working on here at West Virginia University, focusing on using machine learning and simulation to improve legged localization on challenging terrains.
Quadruped robots estimate their motion using onboard sensors, but slipping, uneven ground, and uncertain foot contacts can cause odometry drifts. This matters especially in forested environments where foliage can also reduce the reliability of GNSS, cameras, and LiDAR. We decided to use a Unitree Go2 EDU to test our proposition of whether a learning assisted estimator could reduce this drift across different terrains. We begin with an open source GitHub repository called Go2 Odom, which takes in proprioceptive sensor data and acts as an invariant EKF estimate. We then build a residual one dimensional convolutional neural network to predict corrections to its linear and angular velocities.
We used the high fidelity physics simulator IsaacSim to create synthetic training data to use in our CNN to simulate 2,000 trials of varied motion and diverse friction conditions with an emphasis on low friction environments. Simulation allowed us to collect large amounts of labeled data before testing on the real robot in a time efficient manner.
We then collected 64 synchronized trials with the Go2 across 5 surfaces: concrete, rubber, foam, watery, and slippery, with motion capture system providing ground truth position. This data helps bridge the sim to real gap during model training.
The CNN uses 1 second of sensor history containing 66 inputs such as joint states, torques, foot forces, IMU measurements, commands, and go-to odometry velocity estimations. Every 0.02 seconds, it predicts corrections to linear velocity and angular velocity in all three directions. When deciding the training, validation, and testing split, we decided to use a leave one surface out structure, meaning the network was trained on 4 surfaces and then tested on one unseen surface, and this was repeated for all 5 surfaces.
The plot on the left is an example trial where concrete was the left out surface. Here we can see the CNN can accurately predict the robot's linear and angular velocities, which are then integrated to plot the position data shown. The blue line indicates the ground truth motion capture data, while the red line indicates the CNN that was trained on both sim and real data. In contrast, the plot on the right shows an example of a slippery trial where the CNN struggles to accurately predict the trajectory of the robot. This is largely due to the accumulated yaw and translational errors.
The table shown shows the comparison of our neural network trained on simulation data only, real only data, and a combination of simulation and real data. The addition of simulation provides benefits in some aspects, but proves to be diminishing in others. And such, an ablation study was performed on 2 simulation inputs, accelerometer and foot force sensors. Ablating the accelerometer proved to be hurting the network as it was beneficial for absolute trajectory error, while ablating the foot force sensors proved to actually be beneficial for the model as the errors decrease, and this is likely due to the non-practicality of the contact physics in sim.
This heat map shows that learning improved linear and angular velocity estimation on nearly every surface. Positive values indicate lower error. The main exception was slippery terrain, where absolute trajectory error and relative pose errors became substantially worse.
Our main conclusion is that learning assisted residual correction improves instantaneous motion estimation across most terrains. However, lower velocity error does not always produce lower trajectory drift, highlighting the need for more trajectory aware learning.
We also deployed the CNN onboard so that the Go2 can process live sensor data while recording and publishing corrected odometry in real time. An Ethernet connection is required only to start and stop trials, while CNN processing and ROS2 bagging continue onboard after disconnection, allowing the Go2 to record ROS2 topics in outdoor environments. Future work will focus on refining the machine learning model to improve correction during slip and progress towards outdoor live implementation using GPS data as ground truth reference.
This work builds on prior learning based legged odometry research and was supported by the NSF Undergraduate Robotics Research for Rural Appalachia REU program. Thank you for listening to our presentation.